Okay, so good evening everyone. Let's start the talk. People is fine answers. So the Physics Society of IISER-TVM, abbreviated as Psi of T, is an organization acting under the guidance of the School of Physics and with a lot of volunteers and students. It aims to serve as a friendly platform in the institute that promotes conceptually intriguing and thought-provoking discussions and to facilitate the learning beyond coursework. So today we have Dr. Jutta Kunz from University of Oldenburg, Germany. And I would like to invite Krishnanand from BSNS 5th year to welcome and invite the speaker.
Yeah, Ravikran. So it's my great honor to introduce today's speaker, Professor Jutta Kunz, to the IISER community. Professor Jutta Kunz is a renowned German physicist specializing in quantum field theory and general relativity. She obtained her master's degree in physics from Justus-Liebig University in Giessen in Germany in 1978 and obtained her PhD in 1982. She held the position of postdoc at the Los Alamos National Laboratory in US from 1982 to 84 and subsequently the position of an assistant professor at Justus-Liebig University Giessen in Germany. And finally in 1993, she became a professor at the University of Oldenburg, Germany, where she continues to be a professor till date. Her research focuses on formal aspects of quantum field theory and general relativity. In particularly, she is known for her work on gravity in 4 and higher dimensions, including models of gravity, black holes, wormholes, solitons, neutron stars, boson stars, and boson shells, black rings, black brains in general relativity, and also in electroweak interaction and effective chiral models in QCD. She is a member of one of the co-chairs of research training group on the models of gravity. Some of her works was profiled by American Physical Society's Physics Central site. She has written over a few hundred scientific articles and which have received thousands of citations and has won many awards. So I invite Professor Jutta Kunz on the behalf of Physical Society of IISER-TVM and also on the behalf of IISER community to deliver a talk on black holes.
Thank you very much for your kind invitation. And I must say, it's really a pleasure for me to be invited by students. I think this is a great idea that students organize their own seminars and invite speakers. So yeah, it's really great, and I wish our German students would have this idea as well. And yeah, of course, we've been teaching now since almost a year online here in Germany and probably similarly in India. But I must say, looking at your place at the university, one can become really envious. It looks so beautiful over there, and yeah, it looks really enchanting, like a land of enchantment when I see it. In my lecture today, I would like to introduce black holes to you, and first I will just talk a bit about general relativity and black holes and general relativity to give you some idea what this is all about. And after that, I will talk a bit about black holes and astrophysics, and finally a bit about gravitational waves associated with black holes mainly. So this is the plan. And of course, black holes have received a lot of attention in recent years, and 2 Nobel Prizes. They were very much related to black holes. First, this 2017 Nobel Prize in Physics for the gravitational waves. And then last year we had the Nobel Prize for Roger Penrose here, really for the black holes. Black holes, showing that black holes are really some genuine endpoint of gravitational collapse. And also to Andrea Gees and Reinhard Genzel. And these two, for them it wasn't said black holes, but it was said compact object at the center of our galaxy. Of course, we believe there is a supermassive black hole sitting there at the center of the galaxy. But yeah, so this is what the Nobel Committee said. And I'll come back to that. But first, I'll talk a bit about general relativity and what we do there and how these black hole solutions are obtained. General relativity was formulated in 1915. So 1915, this is more than 100 years ago. And it was done basically by Einstein. Of course, there was Hilbert writing down the action, but all the thoughts, the physics, that was coming from Einstein, and it took him actually 10 years from his special relativity in 1905 to general relativity, where he had finally included gravity into relativity. So you see, it was a very hard feat, and it was enormous, and many people say much ahead of his time what he achieved. So in order to introduce it to you, let's start with things all of you definitely know, and this is Euclidean space. It's a three-dimensional Euclidean space. Of course, I have to use projections in these drawings, always leaving out some spatial coordinates. And so Euclidean space is a flat space, and there, when we are looking at a three-dimensional flat space, we have x, y, and z as the coordinates, and when we measure distances in this Euclidean space, we use a line element. This line element is ds, and you all know how it looks like. Now, with special relativity, there was a unification because the spatial directions were unified kind of with time. And we now had 4 dimensions, 3 spatial and 1 time dimension. And one way of giving the line element then is what you see up here. So CT is entering as the 4th coordinate, but what you see is that the sign in front of time and the spatial coordinates is different. So time is special, and it's the sign that kind of signals out time. And of course, whether we say minus, plus, 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 or plus, minus, 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 I mean, this is a question of choice of what one prefers. And this is the choice I usually take in my papers on general relativity. Working in flat space-time, I normally take the other choice. The only point that is important is to not change signs somewhere in between. So when you're in Minkowski space, when you have added the time direction, then we know in special relativity, we have to look at the light cones. The light cones are extremely important to understand things, and they are extremely important to understand black holes. And this is why I just recall the light cones here. So we have the time direction and then 2 spatial directions. And here, let's say we take again CT. And then we know the light cone is, has 45 degrees opening. And light is moving here on the light cone. And anything else that has mass, any object with mass, any particle with mass, has to be inside the light cone. So this is the past light cone, this is the future light cone, and particles, objects have to move in the light cone. They cannot get outside. If they would want to go outside, they would have to travel faster than at the speed of light. And yeah, that's not possible. So it's forbidden to go outside, and therefore, if we want to look what type of motion is possible, also then for black holes and space-times that are curved, we must check how does the light cone look like. And this is what we're going to do. Now we come to gravity. So from special relativity, we go to general relativity. And yeah, we say, following Einstein, that whatever is in this space-time, mass, particles, any type of energy, this is curving space-time. So space-time is being curved by the energy content. And this is here depicted. We have the Earth, and it's a kind of bending, curving space-time. And we express this again in terms of our line element, but the line element is now more complicated. It's no longer diagonal necessarily, and just no longer have just constant coefficients necessarily, because we have this curvature, and so we have these metric functions, as we say, the metric tensor G mu nu, and these functions can be just functions of all the coordinates. And what we really want to do in general relativity is have a set of differential equations that tells us what this metric is, what the line element is, how we kind of measure distances, separations in space-time in such a curved space-time. So here, these metric coefficients, these are for us the most interesting thing. This is what we are trying to get, and this is what we study for black holes. So when they have certain characteristics, looking at them is going to tell us that we have a black hole or not. And physically, we would say these metric coefficients, they correspond to gravity potentials. So like in electromagnetism, when you do it relativistically, you have the 4 vector, which is the gravitational potential 4 vector. So here we have more, right? We have a tensor, but in a sense, it's the potential, the gravitational potential, but we have many potentials sitting there. And once we know what the metric is, we also can look at motion in this metric. So here we see the moon moving around the Earth, and the moon is trying to follow as a straight path as possible. But straight means, because space-time is curved, that is always going around and around and around. So it's this curvature that is kind of representing them, telling us how gravity acts. So, and this is now the corresponding, let's say, Newtonian second axiom for gravity. We call it the Geodesic Equation. And yeah, we have second derivatives with respect to something like a time coordinate. And so here we have the gravitational field. So it's pretty much analogous to what we know, just more indices, a bit more complicated than what we usually work with. But basically analogous. And this is then it. This is the field, the set of field equations. Of course, this is written in a very beautiful way, I would say. Here, this is in the desert in Chile, and we have there in the mountains all these wonderful, very important observatories, also extremely important Gravity, for instance, to observe black holes and their properties. And now, what does this correspond to this formula? No, it's let's say the corresponding set of Maxwell equations, but not for gravity. So we have a set of second-order differential equations for the metric, for the coefficients of the metric, these g, mu, and u. And here we have the derivatives of the metric tensor, kind of arranged in certain ways so that we have nice properties. We have, as we say, a tensor equation that we get. And here on the other side, we have that what corresponds to the current in electromagnetism, namely the source. And the source is energy and momentum. So it's our stress energy tensor. And once we specify this stress energy tensor, then we can simply solve, maybe not simply always, but in principle we can solve this set of equations, coupled set of partial differential equations of second order, and obtain the metric, and then we know, the whole space-time, its curvature, and we can calculate the motion and study all the properties. So this is what we want to do. We want to solve these Einstein equations and obtain as solutions black holes. Very special, but most exciting, I would say, solution. Now, Einstein, he was writing down his set of equations in 1915, and he thought, I have this complicated set of coupled partial differential equations. One is never going to find an exact solution to this. But just a little later, a German astronomer, Karl Schwarzschild, he found the first solution. And as an astronomer, he was interested in finding the space-time for the solar system. And of course, he just wanted a very good approximation. Let's say he was saying, I consider this whole thing as static. I forget about the rotation of the sun, which is very, very slow. And I consider the sun as something, an object that is fairly symmetric, which is true to very, very good accuracy. Of course, it has a very small quadrupole moment, but this is a perfect approximation. And as you all know, whenever we have lots of symmetry, things get much, much simpler. So no time dependence and spherical symmetry. This made it possible for Karl Schwarzschild in 1916 to find a solution to this set of equations. And basically he found two solutions which he put together. So the first, which is the important solution for us here, was that he simply said, let's take vacuum. No source, let's look outside the sun. Outside the sun, we neglect anything that is sitting there. So we have just vacuum outside the sun. So our stress energy tensor, the source term, vanishes. So T nu is 0. Inside, of course, we can then, after having obtained this first solution with vanishing energy momentum tensor, then we can solve again. So we have this interior part for the sun, where we certainly do have matter, and then we can just match these solutions, and this is it. Then we have a nice full complete solution. So this is what he did, and he obtained then the Schwarzschild solution. This is how it's called, and I'm pronouncing it German since I'm German. I know in the English-speaking world, many say Schwarzschild, but I don't appreciate this too much, because then the S is put to the Schwarz. And I'll give another comment on this soon. But now I'll be talking about the Schwarzschild solution. So just looking at the solution without any matter, it's a solution, right? It's a solution to the full field equation. So we can look at it. Of course, we can say at the border of the sun at 700,000 kilometers, we are going to patch a second solution. But the other solution, the vacuum solution, is a full solution. And we could also be interested in the meaning of this full solution. And this is what we are interested in. Because this full solution, the vacuum solution, this corresponds to the simplest black hole, the Schwarzschild black hole. And let's now look at what the metric of this Schwarzschild solution looks like. I thought I put down at least this formula, because it's quite clear, easy to understand, and then interpret. And so this is what he obtained. Now we see in red here we have this function n of r, the only non-trivial metric function. And now imagine this n of r would not be a function of r, but it would just be 1. And then we would have a 1 here and a 1 down here. And this thing would be just, again, Minkowski space-time. Yeah, Minkowski space-time in spherical coordinates. So this part is not so important for the Schwarzschild black hole. And now let's look at this function n of r, and then we see n of r is 1 minus 2g gravitational constant times the mass of the object, the central object, divided by the velocity of light squared, and the radial coordinate r. So we see when we go far away, this dies off as 1 by r, and this also allowed to make the identification with the mass, because far away one would like to have Newtonian gravity again, and this is how one identifies this. So this is Newton's constant. And when we go closer, of course, we deviate from the Newtonian case, and it gets stronger and stronger the closer we approach. We go towards the origin of our coordinate system. And then we see there can be problems. There can be apparent, very serious problems. Namely, this n of r can become 0. So here we could have a 0 when r is sufficiently small, namely equal to 2gm by c squared, n vanishes at 0. So then we don't have this piece anymore. It's 0. And here we divide by 0. This looks like a major catastrophe, right? Division by 0. This looks like a terrible singularity that we seem to have here. But actually, it's not that bad. But it took people a long time to understand this singularity. So it was termed the Schwarzschild singularity. Now we just speak about the Schwarzschild radius. And then as soon as I use this word Schwarzschild radius, you know, I'm talking about the event horizon of the black hole. But we have to understand why this is an event horizon, what we see there, and why this is not such a terrible thing that we divide by 0. we have actually not a physical singularity there at the Schwarzschild radius. We have only a rather mild, a coordinate singularity. It only occurs because we have chosen these coordinates chosen by Schwarzschild. They give this nice simple solution, but nothing really singular in this catastrophic way is happening there. And we can get rid of this. We can just make a coordinate transformation, and it's typically called Eddington-Finkelstein coordinate transformation, and then the metric is perfectly well behaved at the Schwarzschild radius. So just a coordinate transformation introducing some new time coordinate is going to help us. And we also see that when r is going to 0, some divergence is happening, and this is then at the center, and this is a real severe singularity, and we say this is a physical singularity, it's a curvature singularity, and here really curvature explodes, and we would say our system of equations don't hold anymore. Here at the singularity, we know we should have some theory of quantum gravity, kind of letting us get rid of this curvature singularity. But in this classical theory of general relativity, we do have this physical singularity sitting there at the center. But we need to look now. One more comment, namely, we do have a black hole, and we're going to understand it in a moment a little better. But this black hole has this event horizon, and this event horizon is kind of a border. We cannot look behind, and I'm illustrating this now. But I always think it's amazing, it's really amazing that Schwarzschild, he found the solution of a black hole, and you see his name, it's a German word, and Schwarz is black, so this is black, and Schild is just a shield. So Schwarzschild is a black shield, kind of black, we know, there's nothing coming out, right? And it's shielding also because we can never know what's behind the event horizon. So the name of Karl Schwarzschild could not have been more perfectly suiting that what he found the first black hole. And now let's look at this event horizon a bit closer. And this is an illustration. Now it's an illustration with this new coordinate time, this Eddington-Finkelstein coordinate time. And here we see the light cones. So these are the light cones. This black line in the middle, this is just symbolizing the singularity at the center. And in gray, what you see here, this is the horizon. And we are going up here in time, and we have again spatial coordinates elsewhere. And we see when we are far away from this horizon, from the center, from the black hole, then our light cones, they are just the 45-degree light cones that we know from Minkowski space-time. But as we come closer to the horizon, as we come closer to the black hole, these kind of change, these light cones, and they change their shape, and they also kind of tip. So they bend towards the horizon, they bend towards the black hole. And you see, when we are right at the horizon, then the light cone has one side in the horizon, but everything else is pointing inside direction of the singularity. As we said, any particle has to move inside the light cone, and light or any massless particle will be on the light cone. We see we cannot get out, light cannot get out, nothing can get out, because the light cone, just with one side, is in the horizon, so light will be stuck there at the horizon. It's trying to get out, but it's stuck at the horizon. It would have to be faster than light, but light is not faster than light. And anything else that would want to get out would have to be faster than light. And so nothing can get out of the horizon. And once in there, it's trapped, and the fate is the singularity here for the Schwarzschild case. So this is basically how we can picture and understand.
Hello, ma'am.
Yeah.
This is not in the Schwarzschild coordinates, right? This is in some other coordinates.
Yes, picture? I have made a transformation to Eddington-Finkelstein coordinates.
Okay.
For Schwarzschild
thank you.
coordinates, the time goes to infinity right here. At the horizon, in Schwarzschild coordinates, time diverges. So in these Eddington-Finkelstein coordinates, this doesn't happen. So Schwarzschild coordinates, they don't cover all. Schwarzschild coordinates, they cover just the exterior. But since time diverges in Schwarzschild coordinates at the horizon, we would have to start again with time. So here we are at infinity, and so we have to put a second patch then. And the light cones in Schwarzschild coordinates, they wouldn't look like that. They would just tip over. But this looks much more complicated, and I think in these Eddington-Finkelstein coordinates, it's much easier to understand because one can nicely picture the effect of the light cones. And the time coordinate in Schwarzschild coordinates isn't valid here.
Hello. In that cone, it touches because of that future, past, and everything. It gets embedded into that side, right? Cylinder.
Can you speak louder? I cannot understand.
Because of that, past and future, it gets embedded into that horizon, right? It touches that into the wall of cylinder.
I'm really sorry. I don't hear you. Maybe I have to switch my get out here and increase the volume. Could you say once more? I have very loud volume now.
Hello, can you hear me now?
Now I can, yeah.
Because that cone has future and past light, it touches into the wall of cylinder, so everything gets embedded into that horizon, right?
Because it's in the wall here, yes, and the wall corresponds to the horizon moving forward in time, and so nothing can get out of the wall, and the horizon is really, let's say, the boundary of the black hole, and everything that is inside has to move, necessarily is forced to move towards the singularity, and is going to end up in the singularity.
Okay, ma'am.
Yeah? Okay. This is the basics. I mean, the most important point about black holes, I would say, to understand how the light cone structure changes, so that nothing is allowed to get out and no information is allowed to get out of the black hole. So there's just a boundary of communication. Yeah, so things can get in, but nothing can get out of this black hole. And sometimes one just compares it to water flowing down some drain hole. And then, let's say, there's some boat, and the boat has a maximum speed, and as long as the maximum speed is bigger than the speed of the flow, it can escape. But here, this would correspond to the event horizon. Here, the maximum speed would just correspond to the velocity of the flow. So the boat is stuck there, like the light is stuck there. It can't get out, even though it's trying. It's going in the direction outside, but it's not fast enough. And as soon as it's inside, the velocity of the boat is just smaller than the velocity of the flow. So it's somewhat of an analogy of event horizon with fluids. Now, we have looked at the most important things of Schwarzschild. Maybe I should, since I was asked about time, I mentioned already that kind of time, the Schwarzschild time. So the Schwarzschild time, which corresponds to the time an observer who is far away from the black hole would see, would measure. This is kind of going to infinity, diverging at the horizon. So for some outside observer far away, it looks like nothing is ever going inside. It's kind of everything is getting closer and closer to the event horizon, but is being stuck there. But if we take proper time of a particle or whatever goes through into the singularity, but because one saw this diverging Schwarzschild time, people thought, this looks like a frozen star. Nothing's happening anymore. It just gets closer and closer, and then it's stuck at the horizon. So this is also a name that has many been used in the Russian literature, frozen star for a black hole. But let me now come to the rotating black holes. You see, our last one was just static. But when you want to describe black holes in the universe, we think everything there is rotating. Slowly, fast, no matter where we look, we always have angular momentum, rotation. And if we think of a black hole as appearing as the endpoint of gravitational collapse from some star, the star was rotating, so the endpoint ought to rotate also. So we expect that all the black holes in the universe, they are rotating. And so this rotating generalization of the Schwarzschild black holes, this is called the Kerr solution, named after the person who found it, Roy Kerr. And when you look at when this was found, you see, wow, this is about 50 years later, right? So it took an enormously long time to find a rotating black hole, a rotating solution here that was kind of reasonable and could then be identified with a black hole because we have less symmetry. We still have symmetry with respect to time and with the azimuthal coordinate, the phi, but otherwise we have dependence on two coordinates, not just on the radial coordinate, but also, let's say, on the polar angle, on r and theta. And this has complicated things enormously. And you see, it took very long to find this rotating black hole solution. And what you see here, this is just, let's say, a sketch. And in the sketch, you see important things about this rotating black hole. But I'm not going to give you the formula for that. You see a green region here. This is very, very important, and it has the name ergosphere. So when we come from far away from this rotating black hole, we first encounter this green region, this ergosphere. And then you see this blue line here, and this is the event horizon. So this is the outer horizon of the rotating black hole, and here you see it has been pictured basically as being a round horizon. But this isn't really true. You can imagine that if something is rotating, it's getting deformed, right? The Earth is rotating, the Earth is deformed. The Sun is rotating, the Sun is deformed, even though also very, very slightly. So this black hole is rotating, its horizon is deformed just in the set of coordinates that one usually uses to describe the Kerr solution in a simple way. One can use a fixed radial coordinate, but having a fixed radial coordinate does not mean that it's not deformed. This is something one has to get used to, and it's sometimes a bit confusing. The meaning of a coordinate. So it's a coordinate, but it does not necessarily have the geometric meaning that we would like to simply associate with it. So we have a deformed horizon, and then the inside, okay, for the Kerr solution, we can see what's inside, yes, but we don't really know what's inside for an astrophysical black hole. So the inside may not be so important for this solution, but when we look at it, then we see in the Kerr solution, the singularity is no longer at one point, but it's on a ring. So we have a ring singularity here in a Kerr solution, but we don't know anyway what's in there. What are now the most important new effects? It's very important that there's a non-diagonal term in the metric, a dt term, and this gives rise to gravito-magnetic effects. And what do we see here? We see frame dragging. This is a picture that is supposed to illustrate this frame dragging of a rotating object in general relativity. And when you have Newtonian gravity and a Newtonian body is rotating, then the space around it is not affected. Just the body is rotating in there. But when we have general relativity, the rotating body is kind of dragging the space-time along. No, it's taking it along. In the case of Earth, what is depicted here, the effect has been measured, but it's tiny. It's very, very small. And you see, when we have a satellite that is just trying to follow a path around, it doesn't precisely come back to the same place where it started. It's being dragged a little because the space-time is rotating, and what is in space-time is being taken, dragged along. Now, for a black hole, this huge mass in a very compact, small region for a black hole, the this effect becomes enormous. So when we have a rotating black hole, it's dragging the space-time around it along, and as long as we're here outside this green region, which is again the ergosphere, we can go any which way we like, right? We can go in this direction around the black hole, we can go in this direction around the black hole, it doesn't matter. But as we come closer to this green region, something most amazing happens, namely this dragging of space-time. This becomes so enormously strong that really everything is being dragged along. And what you see here, these little yellow things, these are again the light cones. Yeah? So we have the light cones, and we see even light has to follow the flow of the black holes. So if we had light that was first moving in this direction, coming here, yeah, right at the border, it's being stuck again, yeah, and anything else has to move in this direction. Here you see, yeah, all the light cones are now in the direction of the motion of the black hole. So everything is dragged around, and imagine we have some particle coming up here, angular momentum, the other sign of the angular momentum of the black hole. So it's coming down here, would like to orbit the other way around, but when it's coming sufficiently close, it's being turned around and it has to go this way. And the ergosphere is a very special place because in the ergosphere, energy can be extracted from the black hole. It's this rotational energy of the black hole that can be extracted, and then there are various processes how this can be done. So very interesting, very strange physics that is far beyond from what we know from Newtonian physics. So in the final part, let me talk a bit about the astrophysics and the gravitational waves. Now, do they exist, these black holes? I must say, I personally strongly believe so, and I would say most people in the community do so. And it's just because we know there's gravitational collapse when a star has used up all its fuel. It has to, and it's a huge star with a lot of mass to begin with. Then it cannot become a white dwarf, it cannot become a neutron star, it has to collapse to a black hole. And this is kind of what Penrose showed. It's generic that such a black hole is going to appear at the end of life of some star. And famous example is Cygnus X1. So we start with two huge stars, blue supergiants. One is even a bit bigger than the other. And now the bigger, the more mass the star has, the faster it evolves, the faster it burns its fuel. And it becomes a giant, a supergiant. And then we have a supernova explosion, and then we have a black hole. And when the black hole is sufficiently close to the other star in a binary system, then some of the mass of the gas can reach this black hole, and you see an accretion disk is formed. And from this accretion disk, we get the radiation, we get lots of X-ray radiation, and this is how we can observe such a black hole like Cygnus X1. This X means X-rays. And in this most famous case, and I would say the first that was kind of seen and more or less confirmed as a black hole, even Stephen Hawking, who had betted against it, he conceded then that this was a black hole. Here, yeah, it may have a mass of maybe 15 solar masses, this black hole. And most of these stellar black holes are between a few and 20 solar masses, those that we know from X-rays. Here, I show it to you now in the sky. And this is Cygnus, yeah, you know. And right here, there's Eta Cygni, and very close to it, there's Cygnus X1. But this is a stellar black hole. But what we also have here on this map is down here, there's the galactic center. And at the galactic center, we know there is, or we think we know, this supermassive black hole, ZA star. Now we zoom into it. Here we have Sagittarius, which looks like a teapot, and kind of it points to the galactic center where this black hole is sitting. And I received this a few years back from Reinhard Genzel. And you see here the center, and we zoom in and zoom in. Now this is German. This is 1 light month, and here we have 2 light days, and we have the motion of these stars around this center, around ZA star. And this is this observation of this motion. This is what led to the Nobel Prize last year. And now this was from Reinhard Genzel, and this is a picture from the group of Andrea Gees. And here you have quite a few of these stars and parts of their orbits. And from these orbits, one can determine what is the dark central mass sitting there around which all these huge stars are really orbiting. And then one can extract it's more than 4 million solar masses. So we have 4 million solar masses in a tiny, tiny region. And what else should it be than a supermassive black hole? Of course, I and my group, we are working also on alternatives, like many people. But yes, this is what we anyway believe. But how big would this be then? This 4 million solar masses, how big would our sun be if it would be a black hole? It would have a radius of 3 kilometers. So we can multiply this by 3 kilometers, and then we see it wouldn't be that big, of course, sufficiently big. It would be a tenth of the distance between Earth and the Sun. This would be the radius of this black hole. And these were observations. And of course, this is just an artistic picture. We just thought, calculated how big it really would be. And this is very far exaggerated. It's just public relations to make the black hole really black and visible. Otherwise, we wouldn't see much. So this is when the star S2, this most famous star S2, was closest to the black hole 3 years ago, roughly. And interesting things about general relativity could be measured here. But I would say the really most famous black hole is this one. It's the black hole at the center of M87. And M87, this is the biggest galaxy in our Virgo cluster. We belong to the Virgo cluster. And now this just have an enormously big black hole, which is more than 1,000 times the mass of our 4 million solar masses black hole. So this is really huge. And what we see here is a jet emanating from this black hole with a few thousand light years size. And of course, there's also a jet on the other side, but this is what we don't see this. This isn't as bright. And yeah, here we have the most famous picture. It was everywhere in the news. The picture from the Event Horizon Telescope collaboration of this black hole at the center of the galaxy M87. And what we see here, this dark region, this inner dark region, this is called the black hole shadow. Yeah, and the black hole shadow is a bit bigger than the event horizon. So this dark region is a bit bigger than what we might have perhaps thought. We could have thought this dark region is just the event horizon, but I'll explain this a little more. And what we see around it, this is the accretion disk around this black hole. And just to give you just an idea of the size, I took this picture from a talk last week, which was by the Event Horizon Telescope, and I thought it's so nice because they put in here the orbit of Pluto and then the distance of Voyager, so you have an idea how big this region really is. But let me explain the shadow. Why is this region that we see dark? Why is it somewhat bigger than the event horizon? Now, I've pictured it here, I've taken a picture, so this is what I should say. I've taken a picture for Schwarzschild black hole. And now imagine there's this isolated black hole. But there's stars and whatever gas it's around. Let's take some stars a bit away, and they emit light. And now, when there's a black thing, this black hole is going to capture some of this light, and it's going to capture not only light corresponding to the event horizon, but it's going to capture all the light that is reaching this region here, that's rose, this or pink, whatever region, and so this is called the photon sphere. So whatever light from the outside is coming into this photon sphere, this is going to be captured by the event horizon, and then it cannot come to us, of course. And therefore, this photon sphere is bigger than the event horizon. And this is, therefore, what we see in black. So anything in black corresponds then to this photon sphere, and only other light outside can come to us. And if this black hole is not a Schwarzschild black hole, but if it's a rotating black hole, then depending on under which angle you look at it, it can look quite deformed. So here, this would be the shadow, and you see this is the border of the shadow. And it's deformed because it's a rotating black hole. But also because we're looking under almost 90 degrees. For this M87, we are looking under a small angle, and therefore it looks almost round. Here we have all the telescopes that have contributed to produce this picture, and just to see how great this achievement is. This picture, this is such a small area of the sky that it would correspond to have the resolution of here an orange, let's say an orange on the moon. So you see, this is really extreme what they have done. It's wonderful. We are very much waiting to see the picture of our Milky Way black hole. They promised in a few months, but let's see. And in order to picture black holes in other galaxies, now they have to be big black holes. The further away they are, the bigger they have to be to get a picture. And yes, they are now thinking about putting one observatory into space, to have very, very long baseline, and then be able to resolve even further black holes. I see my time is basically up. I didn't have much time to talk about gravitational waves. But this is the other very, very exciting part of black hole physics these days. When we have two black holes, they orbit each other, and in this orbit they emit gravitational waves, and we can observe them with LIGO, Virgo, with these instruments. And yeah, I started out with this Nobel Prize in 2017. And so when we look at what's happening, then now we see we have first this in-spiral phase when they are coming closer and closer together. Then we have the merger phase, so when they really touch and merge. And then they have formed one object, but this object is still excited, and this has to ring down, which means it's going to emit gravitational waves until it has come to some stationary limit. So it's three phases, and here it's schematically again. Here we see the strain, so yeah, let's say the amplitude of the gravitational waves. Amplitude gets bigger and bigger, and here at the merger it's biggest, and then we have the ring down. So this is how it happens. And what has been observed now by now, we have many, many important cases, but this was the most famous beginning and most astounding beginning, because the black holes were already pretty big. They were quite a bit bigger than what we had observed in X-rays before, and they formed an even bigger object, and three solar masses were just radiated away. Just imagine the energy of three solar masses radiated away in this merger event. So it's absolutely incredible what is happening at such mergers. And here it's pictured down there. You have the X-rays, right? And here, this is the big event that was observed first and impressed everybody. And yeah, these observations earned the Nobel Prize. And then we were getting many more. And yes, this was another very interesting event, because we were reaching with this event more than 100 solar masses. So it's a black hole of 140 something solar masses, which is no longer in the range of stellar mass black holes, but it's intermediate size black holes. But yeah, I think I'm now at the end, and I've taken too much time, but still I will be available for some questions. And thank you very much for your attention, and I hope you enjoyed it a bit.
Yeah, hi. I actually have 5 questions. I hope that's all right.
Yes, please go ahead.
Okay, so when you were talking about the Schwarzschild singularity, you said that the metric is actually perfectly well behaved. What exactly does that mean?
It means that we can invert the metric. Yeah? So there's nowhere anything going to infinity, and the metric, which is a matrix, the matrix is invertible. So yeah, this is what you would like. Yeah? A metric, a matrix that is everywhere well defined, and it's invertible.
Okay.
This is what it means. Yes.
Could you discuss the alternate? I think you call them the Finkelstein coordinates. Like what makes them work as opposed to the Schwarzschild coordinates?
This is I didn't write them down, but this is a very nice trick. What is being done to obtain them? What you do is you look at the light rays. So you look at light rays that are just going radially inside. So we say you're calculating the radial null geodesics. So light rays going radially towards the center. And this is very simple to write down these light rays. And then you say you define a new coordinate, and this new coordinate, this makes here so a new time coordinate such that you have straight lines for the ingoing light rays, radial light rays. So we have straight lines, and yes. That's it. It's no more than that.
Okay, thank you. I also didn't understand why some black holes rotate. Like, do all of them rotate, or do some of them rotate, and why do they rotate?
The black holes that we construct just as solutions of the Einstein equations, they rotate if we want them to rotate, okay. And they don't rotate if we don't want them to rotate. So if we make an ansatz where we have no explicit time, no time dependence, and we have symmetry t to minus t, then yes, we get something that is static. But okay. We can be more complicated and allow for rotation, but it still is stationary space-time, and there's no time depends on the coefficients. Still, it's rotating because we have a dt d-phi term in the metric. So the metric is no longer diagonal, but there's a piece that says dt d-phi. And this is what you can imagine. This corresponds to giving some angular momentum to this thing. If you would make a transformation of some even in our ordinary non-relativistic physics, if you would make some transformation, then rotation would correspond to such a cross term. And the coefficient that can be read off this at infinity, this then just gives the angular momentum of the black hole. But what I mean when I say everything is rotating in the universe, I mean just that when I start with a black hole, and this black hole, when I start with a star, and that star is collapsing to a black hole, then the star has been rotating.
Okay.
Yeah. So when we look at star formation, we have these clouds, and these clouds they they have some rotation, so the central object is going to rotate, and then the planets are forming there in a disk that is rotating, right? So there's always some rotation. And so if the star that was the progenitor of the black hole, if this was rotating, the angular momentum is conserved. It's going to, at least in part, be given to this final object. So the black hole is going to rotate. So I believe that all the black holes in the universe, they will be rotating just because they are formed this way.
Okay.
Is it okay?
Even theoretically, is it possible for a black hole or a star to spin about more than one axis?
To spin about more than one axis, it would not be possible as some stationary object. I think during some transition, yes. I mean, you probably mean some mutation or whatever with this, so that. But then, if you would have some quadrupole moment, it's spinning. It has some quadrupole moment. So you have a changing in time quadrupole moment. And if the quadrupole moment is a function of time, changing in time, then it's going to radiate. So it's not a stationary final object.
Okay.
So in 3+1 dimensions, you can't do that. However, you can go, at least in theory or in string theory, to more than these 3+1 dimensions. And when you go to higher dimensions, keep one time dimension, but allow for more spatial dimensions. Then you can have more angular momentum. Let's say when you have 4 spatial dimensions, so you're in 5 dimensions, then you have already 2 angular momentum whenever you take another plane. So in 7, then you have 3 angular momenta. So in such cases, you can, the more dimensions, the more angular momenta you have.
Okay, and lastly, is the ergosphere theoretical, or like has its existence been proven?
Of course, so far everything is theoretical.
Okay.
However, when we look at these accretion disks, they must, and the jets, yes. So I mean, when we look at the astrophysical environment of a black hole, then we know there's a lot of power going into that, and the long ago, in the 50s or so, the quasars were observed first. And when in the 60s, it became clear these are extremely far away, but they have an enormous output and power. And then it became clear that, it must be some object where a lot of energy can be created, and it's the accretion disks which give a lot of output, but we also think from the ergosphere there's a lot of energy output, and at the moment it's still under discussion. Many people are working on the question, how is the jet powered? Where does the power for this jet come from? And it could be that it's from the energy in the ergosphere, or at least part, because in this ergosphere we can have these processes like the Penrose process, Blandford-Snijek process. We have various processes that in principle allow to extract energy from this rotating black hole to accelerate particles. And in that sense, I think everybody's believing that this is real, but to prove, one would have to observe this, I would say, in much more detail. Of course, there's a lot of progress being made. Proving something in observation science is hard. One can very, very often make some arguments that something else could also be describing this, what one would like to describe, let's say, with an ergosphere, with a black hole, with whatever. Is there proof of a black hole? I don't think so. But there's a lot of evidence. So, in that sense, I think one can accumulate more and more evidence also for the ergosphere.
Okay, thank you so much. Thank you so much.
Ma'am, hello?
Yeah?
So black holes emit radiations.
The black hole itself is black, but it's the environment. So the environment of the black hole, we have here the jet that is being launched somewhere here in the vicinity of the black hole, and we have this accretion disk, and they emit really a lot of energy. So they are the strongest possible emitters that we know of. This is why people in the 60s then really thought quasars must be black holes, because this was the only conceivable thing to explain that one would have such an enormous energy output, so that we would see these star-like things, but at cosmic distance, let's say.
So why don't it reabsorb that radiations?
Sorry?
So why can't that black hole reabsorb those radiations?
Oh, it may absorb some of it, but it depends on where you are, where it's being emitted, and when you emit it just away, why should it absorb it? Now, a black hole isn't some object that is just devouring everything. It's kind of taking that is getting too close. So let's say if the sun would become a black hole all of a sudden, it wouldn't grab anything off the solar system, right? The Earth would just continue on its orbit, the Venus would, Mercury would. We wouldn't receive energy from the sun anymore, but it wouldn't absorb anything in its vicinity unless it's too close. And so what we talk about often is innermost stable orbits. So we can calculate where is the innermost stable orbit, so where can some object stably be rotating around a black hole, how close can it get before it's really attracted by the black hole. And this is very, very close to the black hole. So only when one is coming too close. And this holds for particles and it holds for light, for anything. One has to be really very, very close in order to be absorbed. But for a black hole, like let's say a stellar black hole, before coming too close one would already be spaghettified, right? Torn apart by tidal effects. Like a noodle, yeah, precisely, like noodle, spaghettified. So everything is spaghettified that is coming too close to such a stellar black hole. For a supermassive black hole, tidal effects are not so important because the tidal effects, they would go as 1 over the mass cubed. So you see, when the mass increases a lot, the tidal effects decrease a lot.
So is that all planar or some 3D sphere-like thing that black hole is?
Sorry?
So the geometry of black hole is 2D planar or some 3D like some other spherical celestial object it is? The geometry, you can imagine this is the rotation axis, yes, and now you just rotate around this axis, and this is just a schematic picture to illustrate what there is, but you have to imagine that in principle you have to rotate to obtain not just a cut through the black hole, but the whole thing. So it's the topology of the black hole is spherical. It's like a ball, but when it's rotating, like it's the surface of an ellipsoid. If it's not too fast rotating, because then you even get a dip at the poles. Yeah. So it's always something three-dimensional that you have to picture. Okay.
I should have said that. Thank you.
Okay.
Yeah, I think one just.
And what is n in that equation? N?
This equation?
Yes.
What is the question?
What is n in that equations? N.
What?
What does n denotes in that equation?
This n.
Yeah. Yes.
This n. This red n. Oh, this is just this is a solution. Let's say it's a metric coefficient. It's the metric coefficient here of the time and 1 over of the radial coordinate. And so as metric coefficient, it contains the potential. And this potential, you see, for Schwarzschild, it looks like the Newtonian potential here. When you look at gravity in Newtonian physics, then the gravitational potential is just g, Newton's constant, times the mass of the central object divided by the distance. Yeah, so when you have the Newtonian force, then you have another mass and another radius in there, but this g times m by r, this is just the potential, let's say the Newtonian potential of a mass m. Yeah, so this enters here. This is the whole coefficient. So when we are far away from the horizon, from the black hole, then r is huge, and this becomes very small. So we're really doing Newtonian physics, and when we go to infinity, we just go to 1. Which means we have Minkowski space-time in spherical coordinates. This function determines the Schwarzschild radius. It's 0. and it determines also how fast time is running. Imagine you go to some fixed place. So you take a fixed radial coordinate, a fixed angle theta, a fixed angle phi. Then all of this, because you have fixed these coordinates, all of this vanishes. And then here, this line element, this corresponds just to let's say minus c squared times the proper time, the differential of proper time. And then you can compare proper time to coordinate time. And then you see as you approach the horizon, proper time and coordinate time, they differ a lot. So that coordinate time at the horizon even diverges. And I don't know, have you seen maybe this movie Interstellar? There was this huge black hole, Gargantua, like such a supermassive black hole at the center of the galaxy. And there were some planets, and one planet was very close to this black hole. And on this planet, time was going quite slow as compared to far away here on Earth. And this is also captured by this function n of r. So it also tells us what is then the time delay. How much slower does time go in this deep gravitational potential?
Okay, then we have to overclock our processors when black holes are approaching us, right?
Sorry?
Then we will have to overclock the processors, right? When the black holes are approaching.
When the black hole is approaching us, we will have some blue shift. I mean, these ordinary effects, they are also in here. So we have redshift for things moving out, out of the gravitational potential, coming from close to the black hole towards us. Then they have to kind of climb the gravitational potential, and so they are redshifted. So we have blue shift and redshift. This is all in this function. Yes.
Oh, okay.
Yeah, thank you very much. It was a pleasure, and I must say I was very happy to get many questions. It's always very nice to have some interaction. Thank you very much, and bye-bye.